Hey, folks. All right. Well, why do planets have rings? Why do some planets have rings, I should say? Well, it's all about gravity, right? So, since you've read this and you've read this, right, then the short answer is that when you're really close to a planet, the gravity gets stronger. And if the gravity gets stronger, then the difference in the gravitational pull between the near side and the far side becomes stronger. So strong that you could stretch and strain a moon, or even rip that moon apart and turn it into loose ring material. And that minimum distance, where if you're outside that distance, then the tidal force is weak enough that you can have material accrete and form moons. And if you're inside of that distance, then the tidal force is so strong that the moon would get ripped apart and broken up. That's the Roche limit. And the simple calculation for the Roche limit is that the Roche limit is just 2.4 times the radius of the planet. So in the case of Saturn, what's going on? Well, Saturn has a radius of 58,000 kilometers. So what is its Roche limit? Well, let's do the math here. If the planet's radius is 58,000 kilometers, then the Roche limit is 2.4 times the planet radius. So 139,000 kilometers, which is a big distance, but it's a big planet. So, there we are. What was it again? 139,200 kilometers. Okay. So 139,200 kilometers. If Saturn's radius is 58,000 kilometers, then how far from Saturn is the Roche limit? So what's the distance from Saturn? So it's worth remembering, right, that this calculation for the Roche limit is the distance from the center of the planet out. So that's the Roche limit. Here, it's the distance from the center of mass of the planet, which is at the center of the planet. But if we want to know what's the distance from the planet out to the Roche limit, then that would be this, right? This distance here. So if we just take the Roche limit, subtract the radius of the planet, and that'll give us the rest of this distance. So if we keep grabbing the wrong program. All right. So if we just take the distance to the Roche limit minus the radius of the planet, then that tells us that the distance from the surface of Saturn, or I should say, from the cloud tops of Saturn, out to the Roche limit is going to be 81,200 kilometers. So that distance, how far from the surface of Saturn is the Roche limit? So that's 81,200 kilometers. This table shows the distance. So if this is 81,000 kilometers, the distances to the rings are 16,000 is going to be really close. The D ring is 16,000 kilometers. That's really close. The C ring is 33,000. That's going to be pretty close. 58,000 kilometers is inside here. 78,000 is just inside the Roche limit. So all four of the major rings of Saturn are closer to Saturn than the 81,000 kilometers. So they're all inside the Roche limit, which shouldn't be much of a surprise, right? Because the reason why Saturn keeps the rings, the reason why all this loose, to go back to the picture here, right? The reason why all this loose ring material never did accrete together to form moons is that it can't. It can't accrete together. That the tidal force, the gravity this close to Saturn is so strong that it rips apart anything that's too big, like a moon. So could the Roche limit be responsible for Saturn's rings? Yeah. Right? If there was a ring beyond 81,000 kilometers, then it could slowly but surely accrete together and form moons, which is why all of the major moons of Saturn that you find are outside the Roche limit. All the stuff that's inside the Roche limit stays rings. So how about these other planets? What's the distance to the Roche limit here? For Jupiter, why don't I'll just move this. We can do these side by side here. And I don't think we're going to need this anymore, so I can get rid of that. All right. So, Jupiter has a radius of 61,900 kilometers. So the Roche limit for Jupiter is 148,560 kilometers. What about Uranus? 25,350. So that's only 60,840 kilometers. Neptune's a little smaller. So 625. So if Neptune's a little smaller than Uranus, then the size of its Roche limit is going to be a little closer in, a little smaller. Only 59,000 kilometers. What about Earth? Well, Earth is a heck of a lot smaller than the Jovian planets. So the size, the distance out to Earth's Roche limit is only 15,290, and I'll drop the 0.4. We can round to the nearest whole kilometer to keep things easy. What about these exoplanets? 51 Pegasi b, Kepler 7b, Kepler 22b. These are exoplanets. And hey, since we can use the transit method to figure out the radii of these exoplanets, we can do the next logical step and figure out what the distance to their Roche limits is. So, what did I do? Okay. Got that goofed up somehow. So, write that again, and yeah, there we go. Okay. 51 Pegasi b is a super Jupiter, right? It is, well, that looks like more than 2 Jupiter radii. That's a big planet. So that means it's going to have a really big Roche limit, 325,980 kilometers. Kepler 7b, that's a little bit bigger than Jupiter, so it should have a Roche limit that's a little bit bigger than Jupiter too, 157,560 kilometers. Kepler 22b, more of a super Earth, right? It's about a little 2.5 times the radius of Earth, but too small to be an ice giant like Uranus or Neptune. So 15,290. So that puts its Roche limit at 36,696 kilometers. Why do we do this? Well, because it gives us a sense of if we're trying to study these planets, particularly planets like exoplanets that are harder to study because they're light years away, it tells us where to expect to find rings around the planet and also where to find moons. Because where do you expect to find rings around a planet? Inside the Roche limit. Where do you expect to find moons? Outside the Roche limit. So if we were looking for exomoons orbiting around Kepler 22b, where would we expect to look for these moons? Well, let's look for moons that are farther away than 36,000 kilometers. You wouldn't expect to find a moon inside 36,000 kilometers away from Kepler 22b, because the moon would get shredded and turned into ring material. So, most of the material that could form rings around Earth coalesced into the moon. The moon is 384,000 kilometers away from the Earth. Compare this distance to the Roche limit for Earth, 15,000 kilometers. Why do we have a moon instead of rings? We have a moon instead of rings because all of that debris that accreted together and formed the moon was outside the Roche limit. It's farther away than 15,000 kilometers, and so it could accrete together to form the moon. Well outside the Roche limit, right? 300,000 kilometers, 15,000 kilometers. Was there never any debris? Was there never any material orbiting around the Earth inside the Roche limit? Yeah, probably. There probably was a period early on in the history of the solar system where the Earth had rings, if there was debris orbiting closer than 15,000 kilometers. But when you're that close to the Earth, it would have just fallen back down to the ground. Right? The reason why Earth doesn't have rings anymore is because all of that rock and debris that formed the rings would have come crashing back down to the ground. It got swept up by the gravity of the Earth already, and it's gone. But the debris that was orbiting around the Earth further than the Roche limit, that could accrete together to form the moon. And so it's still there as the rock of the moon. So why do we have rings why do we have a moon instead of rings? Because the debris was beyond the Roche limit, or outside the Roche limit, any way you want to phrase it. So it could accrete. So it accreted to become the moon. Neptune's largest moon, not just one of Neptune's moons, the largest one, right? The biggest moon of Neptune is Triton. It's orbiting backwards, and its distance is decreasing. What will happen when it reaches the Roche limit? Well, what does that mean? It means that if this is Neptune, then when we say backwards, right? What direction do most things in the solar system orbit? Most things in the solar system orbit counterclockwise, right? The planets orbit counterclockwise. Most of the moons of the solar system orbit counterclockwise. Most of the planets rotate counterclockwise. The sun rotates counterclockwise. So when we say that Triton is orbiting backwards, what we mean is it's orbiting clockwise, right? Triton was probably a Kuiper Belt object once upon a time, right? A long time ago, Triton was just another Kuiper Belt object like Pluto or Eris or Charon, orbiting out there, out in the Kuiper Belt, and either it orbited too close to Neptune, or maybe Triton ran into another Kuiper Belt object and it got knocked closer to the sun, and then it passed by Neptune. It got grabbed by Neptune's gravity, and it fell into an orbit around Neptune going clockwise. And the tidal force, the gravitational force between Triton and Neptune is causing it to get closer and closer. It is spiraling in. And eventually, what's going to happen? Eventually, Triton is going to get closer and closer and closer, and eventually when Triton passes inside the Roche limit, it gets too close to Neptune, and Neptune's gravity is going to break it in half. And then those halves will get broken in half, and those halves will get broken in half. And what is now one big moon will get broken up and broken up and broken up by the gravity, and it'll get turned into ring material. Neptune already has rings right now, but when Titan spirals in too close to Neptune, it's going to get ripped apart and it'll get turned into a new ring around Triton. So, what will happen when Triton reaches the Roche limit? Triton will be ripped apart and turned into a new ring orbiting around Neptune. Gravity works the same everywhere. Gravity works the same everywhere in the universe. So if this is how gravity works in the planets around our solar system, if gravity and the tidal force and the Roche limit explains the rings and the moons of our solar system, then we expect it to work the same, well, in weird cases like Triton orbiting backwards, spiraling into Neptune, and it should work the same for rings and moons orbiting around exoplanets. As of today, we've discovered a few exomoons. We have discovered a few moons orbiting around exoplanets. Where do you find them? Well, sure enough, you find them outside the Roche limit. So, I hope that clears things up. The math is easy, right? The concept of gravity and tidal forces is a little complicated, but the nice thing is that the math boils down to be fairly simple. You just got to take the radius of the planet times 2.4, gives you the Roche limit for any of these planets. All right. Post your questions to the discussion board if you got them, and otherwise, have a good day.